AceCo, which is a precision manufacturing for semiconductors, tooling. And he's got about 27 years of accounting and operational manufacturing experience. He is also a Boise State alumni, which is fantastic, graduated with his bachelor's in accounting. After working in the banking industry, probably just like us, many of us will do, be like, why am I doing this? And he went off and started working for AceCo and has been there for 20 years now. In 2016, he was the Idaho Business Review Excellence in Finance Award recipient. So I'd like to welcome Sid.
Thank you. Thank you very much. I did graduate here in '92. I grew up in Oregon and came to Boise on a track scholarship. And for all intents and purposes, this is kind of where I think I kind of grew up. And while accounting is my background, and I'm a bean counter, I can cook books, I can do all that kind of stuff, but the reality of what I really like to do is hands-on things. And when I was hired at AceCo 20 years ago, they hired me as a controller, basically an accountant. But I found that there was a lot of things that I was doing in the operations of the company and really dug into that, spent a lot of extra time on my own to understand how parts are made and so forth, and to gather a technical acumen of the parts that we were making. And I'll describe some of that today. But with that, opportunities opened up for me. And in 2011, our company became an employee-owned company, an ESOP. And our former owners just said, we don't want to run the business anymore. Here, Sid, it's all yours. Have fun. And so while I am a bean counter, I'm now an operations guy, and I love what we do. And hopefully today I can share with you some examples of what we do and how we add value, how we enable our customers to do what they want to do in the industries that we serve. And I'll share with you just a few kind of examples on how that is for AceCo. So just as an overview, AceCo is located right here in Boise, Idaho. There's a couple different AceCos in Boise, but we're operating off of Federal Way on South Geckler Lane. We actually have 5 locations up there, and we're building a 100,000 square foot building right at the intersection, well, close to the intersection of the Interstate and Broadway right now. A big, large building that's being built there. We're going to consolidate some of our work there. But it's been a great operation for us. For all intents and purposes, $50 million of revenue probably doesn't mean a whole lot to many of you, but to AceCo, that's a big deal. We have about 158 employees, I think, today. The highest we were at is about 180. And when I started at the company, our revenue was $3 million a year. So we've done a great job of entertaining some markets that we serve. But our core competencies are machining and repair and refurbishment. For instance, I'll show you a little later some of the components that we machine, some of the machines that we use, and then here are some of the repairs that we do. So we literally take electromechanical devices, seals, robots, valves that our customers use that for whatever reason have failed, and we tear them apart, we clean them, and repair them like new. Whether that be a printed circuit board, whether it be a valve, a bellows, electrical wiring, anything of those natures we can refurbish. Basically, for all intents and purposes, we're process enablers. We add value by creating products that allow our customers to make LCD and OLED displays, semiconductor, memory chips, and microprocessors. That's the industries that we serve. We do a little bit in aerospace, we do a little bit in medical. But just to kind of give you an idea, an analogy of what the markets that we serve, I want you to think about your very first car that you ever drove or what you had. I'm sure that if any of you are like me, it probably wasn't the greatest thing. This was my first car. That was a 1975 Ford LTD station wagon. It got from point A to point B. And at that time, the manufacturing of a car included a lot of human work, hand work, and machining. Matter of fact, the very simple motors that were going into cars like that were built on very simple machines. And in some cases, forging machines, in other cases, stamping machines, and so forth. But that was my first car, and the machinery to make that stuff was pretty simple. What I wanted when I was a young teenager, and as my first car, I wanted this. And I think most of us understand that when you drive a Ford station wagon and you see an Indy 500 car, you definitely want the one that's faster, more sleek, and more cool. But the reality, this is what's happened over the course of about 35 years, is we've seen, instead of having basic machines and basic components to get this car to operate the way that it's intended to do, we've now taken vehicles and gone from getting point A to point B, but adding sensors, adding computers to them, adding features. And all of us are accustomed to those today in our cars. But in order to do that, we had to get away from a lot of the manual work and get into more highly sophisticated machines, simple to say, but harder to do in practice. This machine right here is what we call a dual block. It's a 5-axis machine that can mill engine blocks, engine heads, transmission components that are extremely high complex and tight tolerance. 35 years ago, that was impossible to do. We just could not do that with the machinery that we had. And so the evolution that we've seen in practical things that we use in our daily life has happened also in the industries that we serve. Specifically speaking, back in all the way up to about 1998, 1999, right around there, most of us who can remember a TV was a cathode ray TV. How many of you actually had a cathode ray TV, like that tube TV? So most of you know what I'm talking about. How many of you still have one of those TVs? They just don't exist. But let me describe with you about the evolution that's gone on in making this TV to what we all watch and what we look at today. For instance, this TV, which is a Sony TV, had very to little machining. A lot of the machine components that were used to make that screen were screws, assembly components, stamped pieces such as housings and bezels and so forth, but very little machine components to make any of the work in that TV. Much of those today, if we were to look at the quality of that TV versus what we look at today, none of us would want to go back to that at all. The reality is today we all use OLED and LCD TV screens. And these are extremely complex screens that are very sophisticated and very, very challenging to make. This is one of the areas that we're involved in. We sell components that are used to make LCD and OLED screens to Sony, Samsung, LG, Sharp, Vizio, all of the screen manufacturers in the world. We have components that go into their machines to make those. And for that matter, if you look at the machines that were used to make the old cathode ray TVs and the components there, the complex machining today is much different. I'm going to share with some of this with you today. This machine right here, we have 19 of these at our facility. These are 3 and 4 head milling machines. They are about $990,000 a piece. And we make a large component, which is this component, we call it a diffuser. It has anywhere from 25 to 170,000 holes in it, all different geometric angles to create basically a shower head. It allows material to flow through this component onto glass so that the customers can make a transistor in the glass itself. In order to manufacture that screen right there, the machines that are used to make that screen, which our parts go into, those machines typically cost about $90 million. That's just so that you can get the machine and start producing glass. You still have to make the TV, and that's another complex thing. But in 1998, AceCo was asked if we could make components that were a 1 foot by 2 foot square with about 3,000 holes in them. I'm going to share with you, I'm going to pass around some examples. And so we started making those. What you'll see here, and you just pass it around, there's a cross section. And basically, you'll see a cone on the top, a counterbore drill on the bottom, and a very, very small through hole intersecting those. It basically looks like an hourglass. And what AceCo has done is perfected the way of machining these components, not only from 1 foot to 1 foot, but we are now making components that are 12 feet by 12 feet, capable of making 6 72-inch monitors or TV screens at any given time. Or for that matter, they can take that same piece of glass made on that part right there and dice it up and make a couple thousand iPhone screens or Samsung Galaxy screens. And I'll cover some more about that here in a moment. This is the machine that cost about $90 million. You can see the size of it compared to the individuals there. These are process chambers, all operating under vacuum. Customers like Samsung and LG and Sharp take glass that's about a ½ millimeter thick. They interject it in through a load lock, and there's a large robot that sits in the middle of this machine and moves the glass in between the different process chambers, this one having 5 process chambers. And in each process chamber, under vacuum and in some extreme heat, they lay a deposition of material, a polysilicon or a metal oxide, that then allows them to etch a transistor in it, and for that matter, laying layer after layer after layer and then intersecting all of those together to produce what we all use today. Just yesterday, I just got back from Korea last night. I spent the week over there and saw for the first time a handheld flexible display like this. Samsung will produce this year at the Consumer Electronics Show in Vegas a foldable phone that, rather than having a phone with just a screen like this, you'll open it up and you'll have 2 screens all connected together, foldable and flexible completely. Well, the only way that that can happen is having the capability of a machine shop and other component manufacturers with the ability to make components that make these machines work like they do under extreme tight tolerances. We can no longer operate like we used to under very broad and open tolerances. We are drilling parts, going back to this part right here, 12 feet by 12 feet, with a flatness plane of 10/1000ths of an inch. We drill 170,000 holes on this component here, very similar to what you're passing around there. The intersecting hole is 16/1000ths of an inch. It can be no greater in diameter than 1/10,000th of an inch across all 70,000 holes. And in addition to that, it cannot have a length change more than 2/10. So when you're drilling 170,000 holes, understanding how your machine works is one thing. Being able to drill it and have the correct machining components, that is the drills, the end mills, and so forth, to do that is another thing. That's what we've perfected at AceCo. Here's a diffuser. That is a coupon taken right out of the middle of this diffuser here. If you are carrying a Samsung Galaxy or an iPhone that has an OLED screen, your screen was made on this part. Every single iPhone and Samsung Galaxy that we see is made on an AceCo part. Every single one of them. Typically LG and Samsung and Apple, all of them making those screens. So you can see, here's the blown up cross section of that. Having a large cone with a counterbore, doesn't show the full length of the counterbore, but that intersection right there, and removing and ensuring that there's no burrs at any of those intersections, is AceCo's value. We've spent decades in our company collaborating with our engineers and our machinists and our machine tool manufacturers on how to do this, so that not only do we produce one part, but we can produce thousands of parts, always being the same without change. The last thing our customers want to do is figuratively have a recipe to bake cookies and realize they've got to change the recipe, the temperature, or so forth. And in this case, the complexity of the processing is incredible. In addition to that, AceCo makes other components that are used to make memory chips and microprocessors. I'll pass this one around as well. It's called a faceplate. And through that part, in a machine very similar to what you see up here, our parts are used to lay a deposition onto a silicon wafer. In that matter, customers are able to lay the architecture and the design of the chipset in those machines. That part that we're passing around right there has about $170 worth of material, and at AceCo, that part will sell for about $3,500. We make roughly, maybe 750 of those a month, of all different designs. On a good month, maybe 1,000 of those. But our customers, the Texas Instruments, the Samsungs, the Sonys, the Intels, the SanDisk, all of those chip manufacturers are using our components to actually make their wafer chips, which we use every single day, all of us in this room. And for that matter, this is a new iPhone 11, which, by the way, is an incredible piece of electronics. I have one here, and to see it broke down and look at the complexity of what it can do, not only do we have the flash storage and the sensors here on one layer, we have the microprocessor, the modem, the receiver, and in addition to that, the battery itself. All of that stuff being put in a very, very small, compact design that we carry around with us. The capability of these components now require machine shops to have extremely high tolerance in our machining. The only way that we can allow our customers or enable them to make the chips that they do is to produce extremely tight tolerance parts. Historically, in the last 15 years, chip manufacturers, that's the Sharps, or excuse me, the Samsungs, the Microns, the Intels of the world, were typically laying deposition and memory in a very lateral motion. But now the chip manufacturers are doing all of that in a 3D architecture and going vertical. And the way that they do that is through a series of depositions. So typically on a typical chipset, you can have roughly 250 to 350 layers of deposition, anywhere from 8 to 10 atoms thick, all the way up to a couple microns thick, depending on the application. But the reality of what's happening is you and I, as users of electronic components, are demanding more sophistication, more memory, more processors, more capability. And as a result of that, we want it to be in our hands in a very small area and extreme low heat and processing so that it doesn't eat up the battery. So there's been a lot of demand on machine shops to up our sophistication in the product that we make. So here are some of the other components that we make. So for instance, Gamma shower head. This is used by Intel for a deposition process. For electrode, that's on a Tokyo Electron tool set that's used in the etch process to etch away material to create the architecture on a chipset. And other components. This is a susceptor pedestal, has wiring with a built-in heater to it. That heater can heat up to about 570 to 620 C, and actually the wafer sits on that pedestal and heats it up in the processing of itself. And the top component, this is a Novellus vacuum chuck. We use those or sell those components to Intel. It's made out of a high dense polymer called Vespel. It's made by DuPont. That piece of material right there is about $580. So the last thing you want to do as a machine shop is come up with a process that doesn't work, so you end up scrapping $550, $580 pieces of material over and over. And so we have a lot of demand on our engineers to help and work and collaborate with our machine shop on not only how we design products, because engineers are great, matter of fact, they're extremely good at creating and designing product, but in many cases, some of the stuff that's designed can't be made. And And that's the challenge and the difficult that we have as a machine shop, is taking designs and making them into products that can be produced. At AceCo, we consider ourselves a high-precision machine shop. I've been around enough machine shops to know that there are very few, matter of fact, I don't know of any machine shops that say that they're a low-quality precision machine shop. Everybody says they're high precision, but the reality is that AceCo is extremely high precision. And we use very sophisticated inspection equipment, which I'll cover here in just a bit, to help us understand how we machine. For instance, at our facility, we have an electron microscope that we're capable of taking material analysis and high-resolution pictures to help our machinists understand what they're machining, and also helping our engineers who design these products, these types of holes and features on those holes, to better understand whether or not they're machinable. In this case here, we were trying to put a radius at the top of this cone here, and that radius is very challenging because typically on a radius tool it'll leave a step, and so our engineers came up with a brushing method, a way of brushing with a kind of a brush sandpaper to actually round that edge, and that product is now enabling our customers to make a extremely highly sophisticated touch screen for the medical industry today. High resolution review of x-rays as well as other imaging, otherwise probably not capable had our engineers and our machine shop not figured that out. In this case up here, we were able to take our electron microscope and identify this band that we were seeing in our material. And basically what was happening is in our ultrasonics that we were using to clean the components, we were finding that we were burning the surface itself, which then attracted particles in our customer's process. The only way that we could ever figure this out is if we have inspection tools that help us understand and analyze the work that we do. In addition to that, we work with our machinists and our engineers to identify the best type of machining components today that we can use in our production process to produce the tolerancings that our customers require. I'm going to pass around here in just a second an example of that. This drill right here is 16 thousandths of an inch in diameter, extremely small. And in 2014, Mitsubishi figured out how they could put a hole from the top of that drill all the way through the cannulation of the drill so that coolant could come out right at the tip of the drill, right next to the cutting surface of that drill. And as a result of that, we could eliminate the binding of a drill, the heat that occurred at that drill, as well as the chip breakage that we needed. We were able to produce a much smoother surface with that and the longevity of the part itself. In addition to that, we were able to take our inspection equipment and understand at high resolution how the tips of the drills are wearing in the process. This is a brand new drill. You can see how sharp that is, and after drilling a number of components. And this helps us understand how many holes we can drill with a drill before the quality of the hole that you see here breaks down. I'm going to pass around a drill here so that you can actually see how small that is. If you drop it or break it, don't worry about it. I'll pass another one. But right on the very tip of this drill, I know it's very difficult for you to see. If you'll take the magnifying glass with the front downward and look at the end of the tip, you'll be able to see the holes in that drill and see how small that they are. Our engineers developed a process to understand how we filter the fluid going through that drill, but in addition to that, identifying what pressure we can run that coolant through that drill and effectively cut the material that we were working on. That drill runs anywhere from about $40 to $90 a piece. Some of the higher end ones we use can go as high as $150. When you break 100 of those in a month, it starts to add up. And literally at AceCo, what we do is we go to our engineers and say, you figure this out. You figure out how we can take this drill that can produce incredible sophisticated holes and very high polished surface finish, and you figure out how we can use that in our operations. It's been a great challenge for our engineers, but with the tools that we've been able to be successful at that. In addition to that, we have found that having highly sophisticated inspection equipment is important. And to do that, we have several pieces throughout our shop that our engineers use every single day. And it's expected of them to become experts in some of this equipment. For instance, this over here is what we call an AOI, automated inspection. It can take a plate similar to this one here, and it can take a measurement of the diameter of the hole. It can take a picture of every hole, and if properly programmed, can focus in on the top of the hole and then go down to the bottom of the hole, so the optics through the hole, and then focus in at the bottom of the hole and infer the length difference of that. In this case, we're only talking about 3,000 holes. We have components that are just slightly bigger than that, about 20 inches, that have 60,000 holes in them. That piece of equipment could do all of that measurement and picture simultaneously, multiple holes at a time, in roughly 4 hours. And our engineers are expected to then take the pictures that are taken and the measurements and quantify that to identify if on this part or others that we make, there are certain regions that might have a greater diameter than the other, utilizing the same drill, or the length of that small hole might be different as well. Incredible piece of equipment. It's about $290,000 and takes roughly one engineer to run all the time at our facility, yes.
So the round part there, does it have the 16,000 diameter holes?
I think this one, the exit on this one does not. I think this is a 28,000 hole.
So smaller than that?
Oh, much smaller than that. Who has the drill right now? You do up there. Can you see the holes through there? At the very end of the drill, are you able to focus in and see the holes on the tip of the drill? Any of you are able to see them? Okay. So very difficult to see, but that is a that's a 19,000 drill. Yeah, so when it gets your direction, it's very difficult to see, and if you can't see it through the end of the drill tip, flip it over and look at the back of it, and you'll see the entrance of the holes there. In addition to that, we have a non-contact profilometer. We want to know the surface roughness of the product that we produce. And in some cases, our customers dictate to us a certain RA, or surface finish. In some cases, they want a high RA, maybe 100 RA, but in other cases, they want close to a mirror finish, a 2 to 4 RA. And the only way to do that is to have some type of measurement device that can tell you what you're cutting and what you're machining is hitting that certain surface requirement. So we can not only take the measurement, but we can profile it and understand in a picture view of what that surface looks like. Incredible piece of technology under high resolution measuring. This is a new one for us, a beta backscatter. It allows us to measure coating thicknesses. Much of the product that we produce today gets anodized, in some cases down to a 2 micron anodization, other cases about 60 to 70 micron anodization, and other cases ceramic coatings, yttria spray, rare earth material that's coated on these components to help them last longer in the production field. And as a result, to ensure that the uniformity of that coating is the same throughout the product and it's being applied correctly, we use this beta backscatter to help us understand that. And from there we can develop a map that shows deviations in the thickness of that coating. But of course, the biggest toy that our engineers love is the SEM. It has an EDS XRF. We can do a material analysis. There's not a day that goes by at our facility where we're taking alloy, whether it be a chip or a raw material, putting it under our SAM and identifying the material composition. In some cases, buying 6061 aluminum, which is about 90% of what we use as a substrate for our manufacturing. Many people think that 6061 is just common, but there are certain types of 6061 that have low silicon, low magnesium, and other cases that steel or other alloys that are precipitants in the alloy itself, but still provide certain features for coating and machining. And so we use that all the time to identify what we're doing. I think most of us have probably seen some of those detective shows where they do samples of like a lint, and they're able to trace it back to a cloth that was purchased at a store, and that's how they find the killer kind of thing. Well, we do that same type of thing at AceCo, and we use these tools to back in and help us understand what we're making. So I've been asked several times, where does AceCo add its value? And really, much of the time that I've been at AceCo, we've been operating in this middle range where we've been, accurate at some times, but our precision isn't there. Other cases, we haven't had any precision and accuracy. And over the course of the last 10 years, our focus within our company is moving from this area to where our parts are precise and accurate all the time. Our customers don't want precision without accuracy. They don't want accuracy without precision. They want precision and accuracy all the time. And our engineers at AceCo spend the majority of their time not designing product, but helping us understand how to use product in our operations. That's where the value gets added. Matter of fact, very little value in our company is attributed to the actual design using SolidWorks or some other type of drawing tool. The value is really added by engineers who go out on the floor and work with our machinists on making something that otherwise, typically and historically, has been impossible to machine. And as a result, we've built our business model around making very precise and very accurate parts. And that's the reason why we're dealing with companies like Intel and Applied Materials and Samsung and LG and so forth. That's what they require all the time. So just as an engineering function at AceCo, let me just I think most of us kind of understand maybe what some of the typical engineering protocols have been. And traditionally, what we have seen in our company is that engineering goes through a design process. I think everybody here understands that's why you're here, is looking at how product is designed, and whether it be some of the components that you see that I'm passing around here today or some other type of widget. The design is one piece, but there's a traditional handoff that's been done, whether it be through a print or a 3D model, something of that nature. The engineer hands it off to the machinist, and the machinist spends hours of time, successful sometimes, unsuccessful at other times, trying to figure out how to machine something. The reality is this model no longer works. Maybe it does at some facilities, but at a machine shop or a high precision, high accurate machine shop, this model does not work and hasn't for quite some time. The model that really works at AceCo is a much more collaborative model where we take what we think is the value, a collaboration of teams, that being not only our engineering, but our planning, materials, quality, and our customer, and our manufacturing, and we tie all them together. In our company, neither one of these entities is greater than the other. Our engineers are no greater than our machinists. Our machinists are no greater than our engineers. Our planning is no greater than our quality team. And we expect that we add value by bringing all of these things to the table. And so much of what we do as a company and our success has been built by taking engineered product, which has to be done, and grabbing everything else within our company and collaborating on how we can make that. And that goes back to these components right here. Not only are engineers using them, but this entire team is using those components to identify how we're machining and making the product. This occurs as a collaboration every single day at our customer. And as a result of that, our expectation when we hire somebody in quality or inspection or planning or an engineer is that they have skills to interact and work with others. And much of that means that you have to be out of your desk and you have to be on the manufacturing floor. Our expectation is that our engineers spend no greater than 15 to 20% of their time at their desk. Remember, again, the value at our company is not added by creating and designing, it's added by improving and designing processes. So once a concept is formulated and put to print or 3D model, our engineers work with our manufacturing and other groups to identify how it can be made. Our engineer, our lead engineer today, will spend his entire day away from his desk working with our manufacturing team on how to improve a process. And I'm going to give you that example right here. So we have this hole, which is similar to this plate right here. You can see that there's a counter bore and then there's a long pinhole right here. Our customers came to us and said, we are buying this product from another machine shop and we are having problems with that. And what we're seeing is that there is a restriction of flow through this hole. And we have a highly sophisticated flow conductance meter that we can actually take and seal on this surface right here, and we'll run a nitrogen flow through that hole, and this device will read the feedback or the pressure that's being created by that hole. And even small minor abnormalities, whether that be a restriction in the hole's diameter or its length or maybe a burr, can create a flow difference. And our customers were seeing that restricted flow rate. And we identified that flow rate through our analysis and our engineers being attributed right to that intersection, or excuse me, right at the exit of that drill hole. We drill that hole from this top down through and it exits this surface. And this is what we found. Our engineers identified these small deviations that were being created by our competitor that were creating problems in the manufacturing of microprocessors and memory, 3D memory chips. Specifically, burrs at the top of the hole, chatter marks, and these types of voids, which we have never been able to figure out how those occurred or how our competitors were doing those. Our engineers and our manufacturing folks spent the better part of about 3 weeks identifying and analyzing this product given to us by our customer, again produced by somebody else. This will result in roughly $1.8 million of revenue in 2020 for our company. And again, it's because our engineer said, hey, there's no design. He's not going to be the one that designs this right here. That's already been designed. What he added was a collaboration with our machine shop on how to machine this burr-free. And so again, we took this collaboration team led by our engineer with a group of folks, and he identified this through coolant drill in a different flute type with a different chip rate. Where is that drill at, by the way? Can you see the hole?
Just got it, but
okay.
Not yet.
So in this case, that drill is a little bit different here. This drill, our engineers and our manufacturing team thought that if we could put this little relief right here, and then also this relief here, we could reduce the chip that was coming off of the cut. Rather than a curly Q chip, we're breaking that chip and literally making a powder. That's what it really looks like. The chip is just so small, and when you're only drilling at 16 thousandths of an inch, you can imagine that chip being very small. As a result of that, our machinist, working with our engineers, identified that if we use this tool here, it's called a Fanuc Robo Drill. It's a high RPM spindle, runs at about 24,000 RPMs, and we could adjust the feed rate. That's how fast we push that drill through the product. Or if we use a pecking motion as we drill it, we were able to come up with that drilling algorithm on this tool. By the way, that tool costs about $150,000. We have 37 of them at AceCo right now, making these types of faceplates all day long. But they figured that out in that collaboration, and as a result, produced an absolute burr-free hole. I told you that took about 3 weeks. The expectation from our customers for now, moving forward, is that process happens in 2 to 3 days. And so our whole focus within our company, moving into 2020 and 2021, is absolute speed. And that's a challenge for our engineers. It's an extreme challenge for our production and inspection folks, because typically our experience is each one of those groups wants to dot their T's and cross their I's all the time. They want data, 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 data. And in reality, sometimes the decision-making process, this right here, means that we have to do it much quicker, and we may only have 90% of the work that we want done and still have to make a decision. So if there's something that I can tell you today, is that at least in the manufacturing field, speed and decision-making is highly critical. And doing that very quickly and accurately, understanding and recognizing that sometimes we make mistakes. We're not going to have all the time. You can imagine that if you have 3 days to do all of this work as compared to 3 weeks, that extra couple weeks right there is where we dot our I's and cross our T's. And the reality is that our customers just simply don't have that time anymore. So we try to do things real time, real quick, and it requires that collaboration. I can tell you that from the AceCo standpoint, again, being a machine shop, getting from an education to a job is one thing, but adding value and skill sets in the workplace is never ending. And for that matter, we hire machinists and engineers and quality and other types of inspectors all the time. And quite frankly, about 10% of them are of the model that we want. And the typically is that they come with great education, they have very little experience, but don't want to spend a whole lot of time understanding more about the value that they can add. In some cases, that means understanding and spending time outside of the job function that they're hired for. Again, I mentioned machinists at AceCo and engineers, they don't just simply work at their desk or at their machine. They're constantly working together. But an engineer who doesn't get out of his desk and go out and wear some dirty clothes and maybe some gloves and some safety glasses is never going to make it in the AceCo world, because they'll never understand how a product is made. And so we're challenged with that. Matter of fact, we suffer in our industry not getting enough aptitude and willingness of people that we hire to go out and be a part of a collaborative team rather than just focusing on the things that they've been educated on. There's one piece of advice I can tell you is never stop learning. And I appreciate when our employees come to me and ask. By the way, wherever you end up in your professional career, if you don't ask questions, you'll never hear the word no, and you'll never hear the word yes. And so I love when our employees, engineers, machinists, accountants, custodians, whatever, ask us questions and ask us, can we do something different? Just the other day, I had a machinist come to me and say, Sid, I've been running this machine now for 12 years. It's the same machine. There's another machine over here that can improve the quality and probably improve the process speed by about 20%. It's $145,000. Would you please go buy it for us? $145,000, a lot of money. But let me tell you something. I can't say no and I can't say yes if an engineer or a machinist doesn't ask me those questions. So if there's one piece of encouragement that I can tell you is go to your employer and ask questions. ask them for resources, beg them for resources, but do it with the understanding that you're going to take what they give you and give them a return on their investment. Not only an investment in equipment they buy, but the investment in you, because you're the ones that they're paying to bring solutions to their work. And I guess last of all, I think most of us understand about good, better, best practices and so forth. So with that being said, I'd like to open it up for some questions that you might have. And by the way, did everybody get a chance to look at the drill yet? Okay, what'd you think?
It's pretty cool.
Pretty amazing, huh? Did you see it? You couldn't see it? Did anybody see the hole? A few of you did. I am still amazed to this day that a company can figure out how to put a hole through the cannulation of that drill. A drill that's only 19,000ths of an inch, that drill hole has got to be 4,000ths of an inch in diameter. And if you ever want to amaze yourself, just go out there and look that technology up. It's called through the spindle coolant drills. There's a lot of them in the world, and it's amazing how they figured it out. And by the way, engineers and machinists collaborating figured out how to do that. Go ahead.
From what I've seen, a lot of your products revolve around drilling really small holes. And have you ever looked into EM?
Terrible.
Yeah.
Absolutely terrible.
Okay.
And the reason is that they cannot produce a surface finish as clean and cut as a hole. Even a wire EDM or a sinker EDM, it's too rough.
Okay.
You'd have to go back with a reamer or something of that nature. And yes, we have spent a lot of time and resources. And that whole piece of gray hair right there is EDM. Definitely challenging, yeah. But I got to tell you, great way of thinking here. That's what we expect our engineers to do, is to go out and figure out and question and ask why or how come, or for that matter, take it one step further and say, I did this, now I'm ready to test it. But yeah, absolutely.
So I'm wondering about the viscosity of the coolant that can actually get through that hole. Is it any other coolant or is it vapor?
Well, I can tell you that you're not putting oil through that.
Yeah, exactly.
It's a water-based coolant, yeah. We actually run two different types. One, we run as a mist, so we take that and we run it through a pressure that runs it's hard to explain, but anyways, it creates a mist, and so coming out of the tip of that drill is a mist that sprays, and then in other cases, it's just a straight stream. Of course, you can imagine trying to look at that stream. It's very, very small, but it's cutting right at the surface. Yeah, but typically water-based is the only way to do that.
So are companies using this and putting like aerosols through them? Are they printing like liquid gas or glass? Or?
Through like that drill?
Yeah.
You
Or
know-
not through the drill, but through like the
This,
parts that you make.
typically these are etch and deposition products. And when I say etch, basically what you're doing is the customers, chip manufacturers will lay a photoresist material on the silicon wafer. They'll charge a pattern on it, if you will, a printed pattern on there. And by doing that, it protects the design or the architecture of the chipset. And then when they run the etch process, which is typically a dry etch chemical, that then etches away anything that doesn't have that protective layer over it, which then leaves, if you will, the architecture that you want. Then, of course, they'll use that same type of product in deposit material, whether it be a polysilicon or other conductive material, and fill some of those voids as they intersect the circuits. Yeah. It's incredible. I got to tell you, the very first thing that she said, Sid's a bean counter. I am a bean counter. I know how to machine parts, but the how and the sophistication of how those chips are made is incredible. There's great YouTube videos on how it's done. But the reality is, none of those customers, the Intels of the world, they can't do what they can do without products of AceCo and others. Yeah.
How long would one of those large beds typically take to machine?
That large diffuser that I showed at the beginning, we have the 100K, which is 142 inches by 138. That one typically has 5 operations, and each operation is about 39 to 45 hours a piece. There's a lot of setup time in getting that material lined, especially when you drill a cone here and a counterbore here. When you drill a cone and you flip the part over to drill the counterbore, you can't be off. So the concentricity is so incredibly difficult to hit. The setup of this product can take, in some cases, 12 to 15 hours, where the drill cycle may only be 30. In addition to that, aluminum at temperature, what's it want to do? It wants to expand and contract. And so if you have a part that's 140 inches across, and the temperature swing in your shop is 20 degrees, or you add heat by friction and drilling, even just a couple degrees, it changes. And so we have to, again, our engineers, our manufacturing have come up with ways to chill our tables and chill our coolant so that we can keep the normalize the material. Yeah, it's very, very challenging. And that's that gray hair right there. Yeah. Other questions?
So, Sid, I don't know if you've been down to our innovation studio?
No.
Okay. You've got a few minutes afterwards, I'd like to try to take
Yeah.
you down there. One of the things that we're building for the mechanical engineering department is a studio with machining and forcing students to go in and machine their own parts for senior design and whatnot, and building an entire studio filled with
Interesting.
machine,
Yeah.
all sorts of things, so.
I'd love to see it.
And I
That'd be great.
appreciate you expressing the interest, or expressing what we've been trying to tell the students, is that we're encouraging them to go down there and not just talk to machinists, be the machinists, so that when they go out in the real world, they have a good understanding of it, not only in designing the part, but actually manufacturing and understanding some of the nuances that.
That's a great thing that you mentioned. At AceCo, an engineer versus an engineer who understands machining or has machined parts, there's at least a 25% difference in pay between those two. It's incredible. Somebody who's willing to learn and understand how parts are made rather than just sit and design. Designers aren't going to last at AceCo. It's those that figure out how to make design work and manufacture. But it'd be interesting to see what you have. But there's a lot of jobs in the machining area. And matter of fact, we can't find enough of them. And the value that's being added is that collaboration and how parts are manufactured. Yeah. Any other questions?
When you said you anodize some of the parts, doesn't that change the dimension of the holes, or is the anodizing just on the outer surfaces?
No, yeah. Anytime you anodize, you're going to add material, you're growing material on that aluminum substrate. And when the customers say, I want a 16 thousandths hole, and you're going to put a 2-micron anodization on it, or for that matter, maybe even a half thou, maybe 5/10 anodization thickness, depending on the type 2 anodization, we've got to factor that in our drilling and compensate for that. And for that matter, in some cases, it's easy to get the anodization to grow at the top of that hole, but to get anodization to grow down inside that hole, when you're flushing chemical and creating the anodization properties in a very, very small hole, extremely difficult to do. And so the last thing you want to do is compensate for the anodization growth at the top of the hole, but not inside the hole. Yeah, very challenging.
So on any one of your big parts, are they 100% defect free? Or
I
do you
could-
flag the defects and sell them
Yeah.
away, and the manufacturer uses them and
Well,
figures out
you
how
know,
to work around them?
Just go back here, it'll take me just a second here, back to the big diffuser right there. About 142 inches by 138, something like that, it's close. If we were to ding any one hole here, whether it be on the cone here or down in here or hit the surface, that entire diffuser is junk. Junk. You gotta throw it away. That diffuser right there sells for $82,000. And I have thrown, we call it throwing away an Escalade. You know, it's like throwing away a vehicle. And by the way, I got a scrap yard of them, piles of them. It's extremely challenging And again, the value that we add at AceCo is figuring out how to reduce that scrap and minimize that. It's one thing to drop a tool on there or to have a tool come out of the tool holder, but it's another thing to handle things and move things in our shop. And our engineers develop handling fixtures and stuff like that to help reduce that, yeah.
Are there methods of building that in sections and fusing them together? That way it costs, or it's less risk?
Yes, kind of, but let me use it in this perspective. Let's just say that you were Samsung and you wanted to make a piece of glass that big. You can't have a margin right down the middle of it and expect a customer to buy a TV with a line right down it. And these parts are so sophisticated that they can pick up surface defects of 1/10,000th of an inch on the substrate of the glass itself. So having it being extremely uniform is challenging. And by the way, we've looked at doing that. And in some cases, you will actually see large, at sports complexes and other type of advertising, where they've done something very similar to that, and they've pieced together displays by making the diffusers and doing that, but they do come with a margin. It just looks weird, yeah. Anything else? I will let you know that we have, I believe, 2 tours next week from the Mechanical Engineering School here at BSU. I don't know what the days are, but there are 2 of them. And remember who came in here earlier? I can't remember who that I was talking to.
Is there any flyers available for that?
I can't remember who the
the
instructor that
website.
came in
Oh,
earlier.
it was Lynn Catlin.
Was it Gus Ingster?
That's who it was, Gus.
Gus.
Gus. So if you talk to, I don't know how you connect with him, but he knows the dates, and I'm sure you could sign up. You could literally see this part right here, exactly how it looks. You can see how we run it. I'll show you the machines. It's just amazing to see. And yeah, we welcome to have you there. I got to tell you that in closing, for anybody that's lived in Boise, Idaho long enough, I'm sure that many of you have driven right by our facilities, maybe once or twice, but in some cases maybe 1,000 or more times, and never recognized that right here in Boise, Idaho, we're making parts that change the world, literally change the world in the way that we interact with you people through social media and pictures and the cars that we have. All of that cannot happen without the products that we produce at AceCo. We are enablers. That's where AceCo adds value. It's been incredible. I've loved participating as a company to see that evolution occur and see how we can make things change. I'll end by saying that just recently, my wife bought a 2019 GMC pickup. That pickup has the equivalent of 6 home PCs in its computing power in that vehicle. 6 times. It is the largest component by 6 times 6 of any computer that we own in our home now. Sensors, light systems, ignition systems, everything else that you can imagine. And now with the changing requirements that we have, every new vehicle being produced in the United States and sold, every new vehicle has to have a backup camera. If it has a backup camera, guess what it's got to have? It's got to have a screen. And that's where AceCo adds value. So thank you for having me. Best in all your things.